Okay, so okay, there's some announcements today. Homework 1 is still due this Friday at midnight. There are lab sections this week. There are still 2 of the optional C++ tutorials that Cinda does. The one tonight is in Woodward, room number 2, and the one on Tuesday is in the Learning Center in room 182. Today's plan is to finish up talking about running time and also to start talking about correctness. And as a warm-up, here's a warm-up problem. So this is a piece of code, and it does something, and it looks similar to what we've looked at before, so it's not crazy. Maybe it is. But anyway, the goal here is for you to think about this, to try to see if there's a better name for this code, and also to decide what the running time of the code is. So go ahead. I'll give you, I don't know, a minute or 2 to do that. Figure out what it does, what a good name for it would be, and then what the running time is. Okay, Judy just asked. Everybody good? You figure out what this does, and what would be a better name for this code? Anybody got a better name for this? Yeah.
Get 0 index value.
Get 0 index value. Perfectly good. I'm going to shorten it a little bit. Maybe find first. Find first. Yeah, what it looks like it just finds. Okay, now what's the running time of this code? Anybody got running time? Now, I'd like you to express it in asymptotic notation, and appropriate asymptotic notation as a function of the size of the input to this problem, and the size of the input to this problem is the same as what we were doing before, the length of the array. So if you can do that, that'd be great. Yeah.
O(n).
O of n. Big O of n? Okay, the running time is big O of n. Everybody happy with that running time? Anybody unhappy with that running time? Unhappy. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Unhappy people. 14, 15, 16, 17. Think this is wrong. Where are we at? 19. Oh, a lot of people. You don't like it. What do you think would be a better running time? First of all, is this actually wrong? Is the running time of this program big O of n? How many people think this is wrong? It's wrong. It would be marked off as incorrect. It's okay, you can raise your hand. I'm raising my hand, but I'm not really. Do you remember what the definition of big O is? It's less than or equal to some kind of function that you're talking about, which is the running time of this code, is less than or equal to some constant times n. That's what this claim is, that the running time is big O of n. Well, what do you think the running time is? I mean, the real running time of this is something like 2 or 3, if you're counting lines of code. But 2 or 3 is certainly less than or equal to some constant times n for sufficiently large values of n. So this running time is true. It's just not tight. It's not as small of a function. N is not as small of a function as you could get and still express the running time as big O of that function. What is a smaller function than n such that this running time is big O of that smaller function? Anybody? Yeah.
Big O of 1.
Big O of 1. Big O of 1 is also true. The running time is a constant, so something like 2 or 3. Therefore, it's less than or equal to some constant times 1, like that constant could be 2 or 3. And so this is also big O of 1. And you can't do better than that. This running time is also big omega of 1, because the running time is a constant of 1, bigger than 0, and therefore it's greater than or equal to some constant, like, for example, 1 times 1. So we have now a function 1 such that the running time is both big O and big omega. Therefore, this running time is theta of 1. That's a tight bound on the running time. Yep.
Why? I still don't understand, based on previous lectures explanation, why this function has big O of 1. Like, why does not constant runtime if the number of loops it does is dependent on the size of the array?
Is the number of loops that it does dependent on the size of the array? The point is that when you hit the first index, when I equals 0, this thing gives up. This code hits I equals 0 and it says, nope, sorry, I'm out of here. And it returns. It may not even get to the I equals 0 part, because it could be that the length of the array is 0, in which case it falls out immediately and returns -1. But in either case, it's only doing a constant number of operations. So even though there's a for loop which is trying to fool you, okay, I'm trying to fool you, into thinking that it was going to be something that depended on n, it's really just a constant number of operations. Now, what is not true is that this is not, oops, this is not big omega of n. That's not true. The running time is not that big. Big omega of n says that it has to be greater than or equal to some constant times n, and the running time is not greater than or equal to some constant times n. Okay, that was the warm-up. That's sort of like to remember asymptotics, remember running times. Everybody good? So now we're going to go back to the final step of our process of analyzing linear search, just to wrap things up about what kind of story you want to tell. So the last step, remember we came up with this running time, we came up with asymptotics, that this was an element of big O of n. We probably could even show that this is an element of big omega of n if we were hard pressed to do it. We know that for a fact, but now the question is, what is the appropriate order notation to use? Should we use big O? Should we use big omega? Should we use big theta? Should we use little o? Should we use little omega? What should we use? I mean, why do they have all these different, why do they have so many asymptotic notations? It's kind of annoying. But why do they have them? I mean, each one is serving, each one has a different definition. So like the big O notation is sort of a less than or equal to. It's saying the function, the running time is less than or equal to some constant times n. The big omega is saying that it's a lower bound. It's saying that the running time is greater than or equal to some constant times n. It's bounding it from below. So we have to pick an appropriate order notation to express the running time of this code. What do you think an appropriate order notation would be? Yeah. Big theta because it's most specific. Yes, that's a very good point. We actually know that this running time is theta of n. And so we can say this running time is theta of n, and all bases are covered. Not only do we know that it's less than or equal to some constant times n, but it's also greater than or equal to some constant times n. But also it's a bit of a cop-out. If you're trying to explain this algorithm to somebody, your attitude towards this algorithm determines what order notation you use. So it's the spin that you want to put on the running time. So the real question is, what spin do you want to put on this? So if you want to say this algorithm is great, this algorithm is a great algorithm, you should use it, what order notation would you choose? So you want to say, this is a fantastic algorithm. The algorithm is fast. then what order notation would you use? How many people think big O? How many people think big omega? What we want to say is the algorithm is fast. We want to say its running time is less than or equal to something. So if we want to say that a running time or a function is less than or equal to another function, we use big O. So if you want to say the algorithm is fast, you say its running time is big O of n. So T of n is big O of n. If, on the other hand, you were saying to somebody, look, this is a pretty lame algorithm. It takes a linear time in order to find the element that it's looking for. I've got a much better algorithm. This algorithm is slow. Then you would say T of n is greater than or equal to some constant times n. It's big omega of n. Now, I have to tell you, this is an important distinction. And yet, in many theoretical papers that are written, there is a confusion between big O and big omega. In fact, people use big O in place of big omega frequently, but it's not correct. So I'm hoping that you'll remember, if you want to say something good about the algorithm, you want to say it's fast, use big O. If you want to say that it's slow and you've got a better algorithm, then you say this algorithm running time is big omega of n. It's very slow. There's a better one, a quantum one that takes only times square root of n. Big O of square root of n. Which is kind of weird, but it's true. Any questions about the distinction between big O and big omega? Okay. All right. So this is the summary of the analyzing code stuff. When you want to count lines of code, which is how we're analyzing time, count operations, we're counting single operations as constant time. Consecutive operations, you sum up the operations. When you have a branch and you're thinking about worst case, so for worst case, you assume that the code takes the worst branch. Another way of thinking about it is that you're trying to bound the running time of either branch. If there's an if, you want to say that no matter what happens, no matter which branch is taken, it's not going to take more than a certain amount of time. And then if you hit a loop, you have to sum the number of lines that are executed over all of the iterations of the loop. So if you have a nested loop, you get a sum of a sum. If you have a triply nested, it's a sum of a sum of a sum of executions. So you get these nested summations in your analysis of running times. Now finally, if there's a function call within your code to some other function, then the amount of time for that function has to be added to the running time of your function. So this is all just reasonable. At least I hope it is. You're just basically counting the number of steps the algorithm takes. This is how to do the accounting to do that. Okay. All right. Then the other thing that I want to tell you was some terminology, which you probably already know anyway. So this will be easy. Things like functions that are constants are theta of 1. Functions that are logarithmic are theta of log n. It doesn't matter what the base is because the base of the logarithm is a constant factor. You can change the base by multiplying by a constant factor. Polylog means it's a power of a log. It's like a polynomial, but it's called polylog. Linear is linear. Log linear, nobody ever uses log linear. Nobody. I've never heard anybody say that. I don't know why I put it on the slide. Historical. But nobody does. They just say n log n. Superlinear is anything above linear, but usually smaller than, you wouldn't say quadratic is superlinear, but you would say superlinear if it was something like 1 plus a half or 1 plus a third. If it's larger than 1, then you'd usually go up to something like quadratic or cubic or n to the fourth. And then polynomial is anything that's theta of n to the k for a constant k. That's a polynomial running time. After that, after the polynomials, there's this big jump to exponential, where the exponent is this n, parameter n. And you remember this from like the first time when we talked about running times. Do you remember, like, if the size of your input is 100, do not expect an exponential time algorithm to finish in your lifetime or in the lifetime of the universe. It will take a long time. And that's why they're called intractable. They're intractable algorithms, meaning they're not good. They're slow. Okay, these are just terminology. Now here's the question. There's 3 to the n, big O of 2 to the n. How many people say no? How many people say yes, it's just a constant? 3 versus 2. Don't be fooled. Don't just say yes, because this is a constant and this is a constant. These constants are being exponentiated. So the real test is whether you can say that 3 to the n is less than or equal to some constant times 2 to the n. And the problem is that 3 to the n is something like 1.5 to the n times 2 to the n. And 1.5 to the n is not a constant. So, no. Okay, there you go. That's your asymptotic refresher course. And also, we'll talk about analyzing running time a little bit more, but now is a good time to ask. That's cool. Now is a good time to ask any questions that you might have about this nagging. You have a nagging tab.
Okay, so on the homework, when it's talking about running time, it's like code, lines of code then basically, or?
Yes, in the homework, yes, to bring this down to practical things, in the homework, when we talk about running time, we talk about counting steps of code. So lines of code is perfectly fine. It's a proxy for time. It's not really time, but it's just something that's an approximation. Okay. Okay, so now we want to talk about correctness. So we talked about running time a little bit, but also in this course, analysis involves analyzing the correctness of a piece of code. And this piece of code doesn't even have a name. So it's something that's returning an integer, and it's taking a vector of strings. That vector of strings is a parameter that was passed to this function by reference. So this little ampersand symbol means passed by reference in C++. See, I've subtly shifted from, or not so subtly, shifted from pseudocode to C++. So now I have to talk about the gory details of that. This is a vector of strings that's been passed by reference. What the heck does that mean? Passed by reference. Well, normally, in regular old programming languages, when you passed something to a function, somebody made a copy of it and gave it to the other function so it could mess around with it. This says no. If you call this function with a vector of strings, you are not passing a copy of that vector of strings. You are passing a reference to that vector of strings, which means that the changes that are made by this code right here on this slide affect the caller's version of this vector. So the vector gets passed in by reference. That reference is used to manipulate this structure, this vector of strings, back in the caller's frame. So when the caller returns, when the function, this function returns, that function, when that function returns to the caller, it could have changed the vector of strings. And it will be changed in the caller's frame, not in a copy. Why in the world would you do that? It seems very dangerous. Saves memory, saves time, really. I mean, it saves both. But if you have to copy before you call, then you could be copying for a long time, especially if the vector is very long. So sometimes you want to pass things by reference because you don't want there to be any copying. because of time considerations. The other reason is that you may really want this function to actually modify the thing you pass into it. So then you pass it by reference so that it can modify it, and the modifications are reflected in your copy. You pass it to somebody, they work on it, and your copy magically changes. Actually, there is no copy, it's just one thing. You're just passing a reference. This is slightly different than Java, meaning it's different than Java, meaning it's a big deal different from Java, meaning that, for example, anyway, never mind. There's memory management stuff that we're going to talk about, but we're not going to talk about it today because all we're worried about is understanding what this does. And so I'm just giving you enough information so you can read this and understand what happens. When I compare two strings, that's a comparison that's lexicographic, meaning that if you gave it apple and Appaloosa, I don't know how to spell Appaloosa. If you give it apple and bear, apple comes before bear. Is there anything else that's puzzling you about this code? Everything else pretty much okay? Yeah?
You say lexicographical comparison, so you're specifically referring to the first letter?
No, if it was AA, and then it was AB, AA comes before AB. Yep.
Shorter ones come before longer ones, right?
Probably, because the last character in C strings is 0. So it does the comparison basically until it hits the 0. And 0 is less than, it's all back to like C stuff. Any other questions? Like if you look back at the first slide for this course, do you remember all those dancing TA pictures? They sort of look like this. Weren't they lovely? I made those, and that spells out hi in ASCII. If you treat this one as a 0 and this one as a 1. Isn't that just terrible? It's like I got time to do that? What the heck? Anyway, that's the class you're in, so too bad. Could have taken Cinda's. She actually liked it. She took my dancing guys and put it in hers. Okay, never mind. That's not important. This is important. What does this do? What does it do? And I'll let you think about it for 2 minutes, but talk among yourself, figure out how you're going to figure out what this does. And I have to tell you, if you're staring at it without actually thinking about running it, that's bad. How many people are almost there? Almost. There. Okay, how are we doing? Can we get at least some sort of, if you have an idea of what this code does, I'm not talking about the running time yet, but just about what it would be maybe a good name for this piece of code, what it does. What do you think? Anybody Care to say what this does? Nobody? Yes.
Lexicographically first after B.
Lexicographically first string in the array after B.
Yes.
Excellent. That's exactly what it does. What should we call it? We can't call it lexicographically first after B. Let's call it find min. It's finding the minimum string, the smallest string, in the vector A of strings, but starting at location B. So it first of all does a little bit of storage, stashing away of interesting stuff. So it stashes the index B into the variable R and stashes the string A of B into S. So R and S are sort of going to be they sort of track the minimum. And then it goes into this for loop and it says, is there anything that's going to beat the current minimum? So it starts off at I equals B plus 1 and it goes down from I equals B plus 1 to the end of the array. And at each iteration of the loop, it says, if the string in AI beats the string in S, as lexicographically earlier, then let's switch. This does the switch. Let's track the new value. Track the new min. If it finds a new min, it tracks it, puts it into the R and S, so it just keeps track of those. And at the end, it returns the index of the string that's the smallest, the lexicographically first. Hard to say. Yeah.
Sorry, could you just define what lexicograph means?
It just means in order of the alphabet.
Okay.
So you always do, like, you're looking up something in the dictionary, the ordering in the dictionary is a lexicographic order. Eventually, people won't know what dictionaries are. But I think you guys, you're still. This is what this course is about, actually. Even if there's no dictionary, there's still a reason to store things in lexicographic order. Okay, so correctness. Is this correct? Does the algorithm actually do what we claim it's doing, finding the minimum? How would you convince somebody of that? How would you argue that this truly finds the smallest element in the array A, smallest string, from B onward, choosing from B onward? I mean, the problem is that there's something going on here that's it's like it's working its way towards being correct, right? At no earlier time in the code is it actually necessarily correct. It's only when it reaches the end of the for loop that it's correct. And you have to yet make some claim about progress towards being correct. Do you see how that's a little bit difficult? I mean, there's a loop that could execute an arbitrary many number of times because the string could be arbitrarily long, and yet you have to sort of measure its progress somehow. And that's the tricky part about this piece of code. And so I wrote down the following in English for why this is correct. The min so far is this string S, which is identically the same as always. It's always kept to be the same as A of R. The min so far is that. And this so far, this is like the progress that's going along here. You've gone so far along the array, and you've claimed that in that point the min of all of this is the min of the min so far. It's the min. I don't want to write any more because then I'll start writing math, and then I don't want to write math. So min so far is S, and so far means of strings in A, B through I minus 1. And this is a kind of a statement that we can make, which we can argue about being true as each iteration of the for loop executes. So the notion of what so far means, how far we've gone, increases each time we do an iteration of the for loop. But this property that the min so far, the min of what we've seen, is stored in S and has the index R, that property persists. That's the hope. This is called, sort of appropriately, a loop invariant. And this is a very crude statement of a loop invariant. It's stated in English. It's not as precise as one would like to have it be, but at least what I would like is that you get the flavor of it. Like it's a statement that's true, but it's true for many iterations as you keep going. Does that make sense? No. All right, fine. How would you prove such a statement? What tool would you use to prove this? Where? You? Yeah. Proof by contradiction. Suppose it fails at some point, and then prove there's a bad thing that's happened. It's good up until a certain point, and then it fails, and then you can prove, hey, actually, that wouldn't be bad. It would work. But I'm not going to prove it that way. But it would work. No, we won't do it because it will.
Just having like a good amount of tests to run this against.
Ooh! Oh, this is great. Why don't we just have a large number of tests to run this against, and if it passes all the tests, then we're happy. How many tests would you like to run?
Considering all the branches and all the cases.
Cover the code coverage. Okay. So if we cover all of the statements, if statements actually get executed during our tests, if every statement gets executed, then that's comfortable. That's good. No, not for me. I'm more pessimistic than you are. I think that even if you execute all of the code, it still could be incorrect. If every line is touched by code, still may not be good. And we're even in a situation that's better than somebody who needs to test their code, because we actually have a statement that we believe to be true, and if it was true, then it would prove that our code is correct. Now, this is pseudocode, right? This is not on a computer. When I go and I type this into the computer, there's a 95% chance that I will mistype one of those characters, and when I run it, it will crash. But the compiler will tell me I did something wrong, probably. If it passes the compiler and it still crashes, it's something that I understand how to do, is check for syntax errors. Believe me, I know how to do that. Proofs are stronger than tests. To prove it, I would be happy with it. Now, what you could have said, and I'll just keep playing devil's advocate here, why don't we just get an automatic theorem prover to prove that this code operates correctly? We could write down exactly what we want this code to do in a sort of a language that a proof verifier could verify, and then we could just run the proof verifier and it would say chuffa, 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 yes. That's exactly what I'm preparing you to do. The definition, this loop invariant, the statement that we came up with for why this code is correct, this is the sort of thing that needs to be given to a proof, a verifier. It needs to be told, this is what property I want this code to have. I want it to be the case that this is doing something like this. Now, it could be that it's a different syntax for representing it. Probably it is. It could be that it's actually a higher level goal than what it is here. But that's a very reasonable thing to want to do, is to get a theorem prover involved, because you don't want to go through all that proof stuff. Nobody does, really. Well, they do. But you need to know what to prove. And that's part of what we're doing, is figuring out these loop invariants. There are other hands up here. Yeah. Is your hand up?
Yeah.
Yeah.
Proof by induction.
Proof by induction. You know, this is ideally suited for proof by induction. Why? Because you have a loop. The loop executes a number of times. You have a property that you want to be true for all executions of the loop, for all iterations of the loop. And you know that it's true at the beginning. And you know that one step of the loop preserves the property, or at least we have to prove that, but one step of the loop being a comparison to the ith element in the array, and an update of the new min value if necessary. One step of the loop preserves that property. It's like an inductive step. This is exactly induction. This is a loop invariant, and loop invariants are typically proved by induction. So we're going to try to prove this by induction. Of course, we can't prove this by induction, this statement that I've written here, because it's got all these so fars in it and weird things, but we'll sharpen it up a bit. Any other questions about this or comments about how this might be analyzed or might be shown to be correct? I mean, exhaustive testing is also an option if you have a small universe of possible inputs. But it doesn't work for infinite universes. Okay, what's the runtime of this? This should be, let me just ask you, was it easier to understand the running time of this code, or was it easier to understand how to prove this code does something that you didn't quite know what it was? Which was easier, running time or correctness? For this piece of code? Really? You don't have a, okay, maybe they're the same. I think that running time is easy for this. Now, there is something that I wrote in here while you were all busy thinking, which was this: assume this is constant, this comparison of strings. This is a cheat, because actually it takes time to do a comparison of strings. It takes time potentially proportional to the length of the longest string. If they happen to be the same length, they have to compare all the characters in order to come down to the fact that the last character is the one where they're different. So this is really not constant time. It might take time proportional. That's proportional to the, let's say, m, the length of the string. M is the maximum string length. There's another parameter here, which is b. And you don't actually go looking at all of the elements in the array. You only look at n minus b of them. So what do you think the running time of this code is? I mean, suppose that you didn't make this assumption that this is constant time, but it took time at most m to compare two strings, and suppose that you wanted to include b in your running time. What would be the running time of this code? Anybody? Big O of n. You're assuming m is constant? M?
N.
No. I know, you said big O, you said this. I was expecting.
Are we assuming constant time, or are we assuming that?
I was assuming it was something like this: n minus b times m.
Which case it would be
Oh,
worst case for n is that it's largest, or that n is its largest.
Good question. So, first of all, this has three variables in it. N, B, and M. The definition of big O only speaks of one variable, N. The reason is because that's the variable that's assumed to be the one that's measuring the growth of the input size. And the goal of the asymptotic notation is to understand how the time degrades, how much the time increases as n gets bigger. Here we have potentially 3 variables that could be increasing as n increases, or as the size, whatever we want to call the size, increases. It could be that we are thinking about a fixed length array, and we're thinking about strings that get larger and larger and larger, but always the arrays of size 17. In which case our asymptotics would be talking about m, and it would be something like order m, where n is 17 and b is something, who cares, because it's smaller than n. Or it could be, which is what I believe is the case, n is what we're measuring as the growth variable. The number of strings is getting bigger. We're interested in the performance as the number of strings gets bigger, but as the strings get bigger, their size doesn't get bigger. M is constant with respect to n. That's a reasonable assumption. Maybe. And the other option is what you said, which is that, well, what happens if the number of strings is proportional to the size of the strings? So then you have this parameter n, which is measuring the number of strings, and the size of each of those strings is n as well. Then this running time would be something like n squared, if b was small. Or it could be that they both grow independently of each other, and we have to come up with a new definition of big O that handles 2 variables that are increasing, which we're not going to do. We could, but we're not going to. Yeah.
I'm just wondering, like, for the lexicographic comparison, like, is it kind of similar to like an n, where like once it finds the first one that like wouldn't work in the string, like it would just stop?
Yep.
Okay. So, but then in that case, like, you wouldn't have to worry about the max string length, right? Because like, since you're comparing everything against the shortest one, you only have to like say like the shortest one's only like 4 characters, right? Like once you get past 4 characters, like you just stop. Right?
This is true. That's a good point. What happens if the shortest one keeps changing? Like the first one that you pick up has length n, and the next one that you pick up is length n minus 1, all a's. The next one is n minus 1 a's. The next one is n minus 2 a's. I mean, what you said is true. If you pick up something that's 4, then it's only going to be 4 comparisons that you're going to need, at least unless you run into something that's smaller and it's really, really long. But it's also possible that the running time could be order n squared. So you see why?
Yeah, because like the worst case is you could have the very longest string at the start.
Right. Or you could even have a short string at the start, but then it gets beaten by a longer string that all begins with a's. So you could go, who knows what happens. It could just be the case that some evil person decided to give you this sequence of strings that are such that you keep changing your mind about what's shortest, and that is no longer a constant length with respect to the length of the array. Isn't this really tricky? That's why I wrote down, let's assume that it's constant. Let's assume that the string length is a constant with respect to the number of strings. But I also didn't want to just like sweep all this under the rug, claiming to you that this is all so simple you don't have to worry about it, because you do. If it is the case that the number and size of your string are related, then you do have a problem. You could have a quadratic algorithm. Okay, but if it's constant, then we're in this situation, order n. And if we wanted to include b, we could call it order n minus b. And we might want to do that later. But in any case, there are 3 parameters, and you have to think about what to do. Think about what's the growth variable. Typically, I have to tell, okay, if you're worried, like on the exam, am I going to know what the growth variable is? Yes. But this is just for your education, like dealing with stuff. Okay. So we got the runtime. Okay, good. Let's get a little bit more precise version of our loop invariant. This is a more of a map. Okay, let's call this something like find min. This is a more of a mathematical statement. It just says the loop invariant is this theorem that the actual loop invariant is the statement in this theorem that says that S, which is identically equal to A of R, that's the rth element of the array A, is the minimum in the entire set of strings E through I minus 1 at the start of iteration I. And we would like to show that that loop invariant is true for all values of I ranging from b plus 1 to n. Does I ever reach n? I mean, it's a yes, no. Does it reach n?
No.
No, it stops. This loop never executes when I is equal to n, but there's a test in this loop to see whether I is less than the size of the array, and that test has to fail for it to fall out of the loop. So it actually is the case that at the start of iteration I could be n. At the start of this iteration, I is n, and immediately this test fails. I less than size of. So the loop doesn't execute, but at the start of the loop, I is equal to n. Why in the world am I dragging you through this at 3 o'clock, no, 10 to 3, on a Monday? What's the point? Why would I want this to be true why would I not want to replace this with n minus 1? Why would I want it to be true at I equals n? Yep.
Worst case scenario.
Not worst case, but if it's true at the start of the iteration n, and then the code says, time to give up, where does it go to next? Oh, here. It returns R. That means that if my loop invariant holds all the way until I equals n, then what do I know when the return value kicks in? I know that S is A sub R, and it's the minimum of A, B through n minus 1 at the start of iteration n. And what's the minimum of B through n, of A, B through n minus 1? It's the minimum. It's exactly what I wanted. I want the minimum of all of the array from B on, which is B through n minus 1. I want that to be the return value R. And so I'm insisting that this, so this is not what I'm going to write here. I don't want, well, I'll screw it up. I don't want to stop at n minus 1, because that's not good enough for me to prove correctness. It's true for the loop invariant, but it's not good enough for me to take the next step to correctness. Okay. So next time we will prove this. Let me just say that the proof for this loop invariant and the statement, the precise statement, is on the course webpage. Under the lecture notes, there's it says proof. At least it should. I'm pretty sure it does. And you can look at it there.
In the whole, do we need to show our root in like the last problem?